or the only contents that you have to worry about chapter 5 are temperature scales, linear expansion of materials due to change of temperature, and the first law of thermodynamics, which is very simple. I mean, let's just put the whiteboard here. Let's see. There, right? Looks different. I think they move it. There. So you have to remember that we use three temperature scales, which is Celsius. We use that for heat, right? And for linear expansion as well. But we also have the Fahrenheit, which is the one that we use in every day here in the US, the Fahrenheit scale. And we have the Kelvin scale. The Kelvin scale is the one that we use normally in science. The basic transformations are that a Kelvin is equal to degrees Celsius plus 273, which implies then that the absolute zero, when it's 0 kelvins, right, the absolute zero, which is the temperature at which the molecular motion totally stops, the motion of the atoms, anything stops, it's minus 273 degrees Celsius. Just so you guys get an idea, the temperature of the universe, right? Remember, the universe is around 13.8 billion years old. And since the Big Bang up until now, due to the expansion, the rapid expansion, has cooled down a lot to the point where we know we can measure it to be approximately 2.78 kelvins. So around minus 270.2 degrees, right? It's very, very cold. So for Fahrenheit and Celsius, the conversion is Celsius over 5 equals to Fahrenheit minus 32 divided by 9. Right? So why do we use Celsius though? So why is Celsius more, right? It's because we have the 0 degrees and we have 100 degrees Celsius. We calibrate a thermometer using the freezing point of water and the boiling point of water. And then we divide by 100 equal units and we get a thermometer, right? And where 1 degree Celsius is the basic unit. So that's why, right? We have these two guys. Then we explore linear expansion. So linear expansion, right? It's the idea that objects, and not just linear expansion, because we do have situations where liquids, when they are heat up a lot, they can overflow a container. That's because there is also an area and a volumetric expansion. But for now, we're just focusing on the linear expansion of objects. And the linear expansion is due to a change of temperature and a coefficient of linear expansion alpha, which is in 1 over degrees Celsius, right? We say that the change on length of any object due to a change of temperature is the initial length times the change on temperature times the alpha, where alpha is a coefficient, is a constant, right? Applications for real life is when we, as I mentioned, when we build railroads, right? So to study, so we have studied water, but in this chapter we study the other states of matter. We study solids in this case, but we also go into gases, a little bit of this, right? In gases, we introduce some of the laws that you should know. Boyle's law, which is that P, the product of pressure times volume of a gas, is a constant. And then we have Charles' law, where the volume divided by temperature is also constant. If we join them together, we get that PV over temperature is a constant equal to the number of moles times the ideal gas constant, right? But why do we do this? Because then we introduce the first law of thermodynamics. In the first law of thermodynamics, we do use expansion and compression of gases. So for the first law of thermodynamics, I gave you the thermodynamics. We use that the heat given or extracted from a system is equal to the work done or by the system plus the change of internal energy. All of these are in joules. They're measured in joules. So heat, right, it's measured as a change of temperature. But remember that heat flows from a hotter spot to a colder. So you can provide heat to an isolated system. For example, I can give you here a container, and there is a piston here. It's a mobile piston. We assume there is no friction, of course. And we say there is a gas. So if I provide heat, right? If I provide some sort of energy in form of heat, then this might actually expand. By expanding, it does some work against the piston. So the system is doing the work. So you can just say that the heat is equal to the work done by the gas plus the change of internal energy. And what is internal energy? Internal energy is the addition of the kinetic and potential energies of the system, right, of the molecules. In the case of temperature, remember, the temperature is a measurement of the average kinetic energy of the particles. So we put it here, temperature is the average, it's different, right? Kinetic energy of particles. So it depends on the motion. Whilst the internal energy depends on the total amount of energy. So that's why internal energy can be negative, because you can be losing, right? And I give you the example of you in the gym or playing a sport, right? You are releasing some energy by doing some work. So your change of internal energy could be negative or positive, depending on the exercise, right? So that's the simple part, right? What you need to know for the quiz is to at least be able to understand that the first law of thermodynamics is no other one than the conservation of energy. For an isolated system, it can be a system with a gas, expanding or compressing, that the work can be positive or negative, depending on who is doing the work on who. The system doing the work or the external force. And then Unfortunately, we don't really do processes, because to understand thermodynamics, right, which has to do with those laws, Boyle's law, Charles' law, right? For example, Boyle's law, it's proving at constant temperatures. We call that an isothermal process. But Charles' law, it's done at constant pressure, which we call an isobaric. So you don't really need to know those terms. But just for you guys to know, if you read it on the textbook or in another resource, which by the way, something that I've been telling students also in school, is that due to this online situation, you guys need to know, need to learn how to find resources, right? If you are stuck, most likely where you are stuck at has been done previously by other students, by professors, and you can find that information, right? And then you can try to cross out information and see if what you are doing is correct. For example, what I want to show you right now with that question about that lab, which I actually found it very interesting. If you're doing the lab on this, or you already did it, then you know that I don't think you did a lab involving this. The lab should have been about heat itself, right? And change on temperature. So what we call the Joule's relationship or law, where you actually relate calories and joules, right? Because once you finish with all this, then we go into what is heat and transfer of heat. So we did conduction, convection, and radiation, right? And once we go over that, we can talk about heat itself. And to understand heat, we need to introduce the idea of a specific heat capacity, all right? So now we know temperatures, temperature scales, so we stay with Celsius, and we can go into the meaning of heat, which is energy, transfer of energy. So to understand heat, we need to introduce this constant, this value, C, which is a constant depending on the substance, is the specific heat capacity, which is measured in joules per kilogram Celsius. And we know that heat is proportional to this value C. Now, what does this value C means? Which I might ask in the exam or in the quiz. The specific heat capacity is telling you how much energy in joules you need to raise 1 kilogram of a substance by 1 degree Celsius. So that is what this means. So obviously you need that to compute the value of heat. You also need the mass of the substance and the change of temperature. Notice how I label temperature with a capital T. That's because lower T is used for time. So we can write the equation for heat is equal to mc delta T. You know what's interesting is that you can have negative heat, technically. It's energy. Talking about negative energy may not make much sense, but if you extract energy to freeze something, right, you are lowering the temperature. So technically this will be negative, right? The idea is that the change on temperature can be positive or negative. And the change on temperature measures a change on the average kinetic energy of the system, which implies a change on the particle speed, right? So kinetic energy depends on the speed. The faster the particles are moving, the more temperature they will have. So I introduce heating cubes, right? So in your X and Y axis, you can put here the temperature in Celsius, and you can put here the heat in joules. And we can say that you have some ice heating, melting, heating, boiling, and then keep going up. And in the lecture slides, there are the names, right? This is called fusion or melting of ice. And this is called boiling or evaporation, all right? When you go from liquid to steam. And that's what we studied last class. So now we can introduce that, or I introduced, but now we can work with that idea of latent heat. And then we can go into thermal machines, which is the last section of this chapter that you're going to be tested on. Now, latent means hidden. So, when you have these horizontal lines, there is heat without a change on temperature. So what did I say about latent heat? I said that latent heat is the heat or energy due to a change of potential energy of the system. Now, what is potential energy in the case of a substance like water or alcohol or any product, right? It can be also solid that is about to melt. Like, for example, if you're melting iron at very high temperatures, right? The change of potential energy means that the bonds that connect a solid or any molecules are starting to break down and dividing those molecules and then melting them, or in some cases evaporate, boiling them into steam in the case of water. So this change of potential energy is the reason why we have this and this. We call that QL equals to the mass of the substance times the latent heat. We're not going to do the very complicated problems where you have to analyze. For example, a typical problem on this will be, let's suppose I give you this container of water, right, or Gatorade. And let's suppose you left it in your car during summer. It gets very hot. So the question I can ask will be, that is asked, right? How much ice, how many cubes of ice, or how much ice you need to add so the temperature rises. But you have to remember that the ice will melt. So there is an extra process besides ice heating. You melt the ice and then it heats. When ice melts, it becomes water. That is a phase/state change, right? So we are not going to do that, right? The only thing I'm going to show you is to compute how much energy you need to either melt or evaporate something. So how do we know that? It's because we do need some values here. So let me see if they're in the slides. They are not. So how about if I just give you that? Now, let me just double check. So we are going to, So the constants, at least for water, because they depend on a whole bunch of The same as specific heat capacity, right? Oh, by the way, remember, the specific heat capacity for water is 4,186. Sorry. Yeah, 4,186 joules per kilogram per Celsius. And in calories is 1 calorie per gram per Celsius. So that is a very important result, because if we combine both, we get the relationship between calories and joules. Why do we need that? Because sometimes what happens is that you heat water by mechanical means. For example, in a waterfall, right? Or in the experiments that you guys did, well, you didn't do it in the lab, you did a simulation, right? But if you want it here in the lab, you will be given a device, a calorimeter, and then another device where you will heat up water, and then I think I explained you this, you will heat water to some temperature, almost a boiling point, and then you will be able to measure the energy from the heater and the energy by MC delta T, the equation there, right? And what you get, or one of the important results, is that 4,186 is equivalent, joules per kilogram for water, okay? Celsius is equivalent to 1,000 calories per kilogram Celsius. So that tells you that 4,186 is equivalent to 1,000 calories, or that joules, right? So 4.18 joules are equivalent to 1 calorie, right? It's one of the results. Would I ask you this? Maybe not to memorize it, because I will give you that, but maybe I will give you values in calories. Let's do a problem with latent heats, and then I will do a couple of problems on, or one problem, so I already did one last class on heat, and then we can talk about thermal machines and just wrap up this chapter. Why did I erase this? Okay. Yeah, here. Chapter 5, lecture slides. The last set of problems here. There one here, waterfall. Let's help you with this actually. I want to do it similarly. I want to give you ice. I want to melt ice, and then we're going to boil water, all right? We're going to just keep same mass. So how will you compute the energy to melt ice? So first of all, we need the latent heats. The latent heat for fusion, which is the same as the latent heat for melting, and it can go the other way around. Ice to water, water to ice. That's equal to 33.5 or 0.4, depending on the textbook that you get or the resource, times 10 to the power of 4 joules per kilogram. So if I want to melt 400 grams of ice, that's important, by the way. You need to make sure that the ice is at 0 degrees. If the ice is not at 0 degrees, which is possible, by the way, you need to heat the ice first, and then you melt it. Again, that is not one of the goals, although you should probably try to figure that out, but for now, let's just give you something like this. It could be a nice sample exam / quiz question as well, or maybe an exam. So how will you melt this? The way you will melt it is just applying that equation there. So you will the energy to melt will be QL, right? Is the mass of the ice times the latent heat of fusion. The only thing you have to do is to change this mass into kilograms. So the energy will be 0.4, because that's 400 grams, so 0.4 kilograms, times 33.5 times 10 to the power of 4 joules per kilogram times kilogram. Kilograms will cancel, and then we will get our nice value, right? 134. So something that you should know is that the energies to melt and to evaporate, even to evaporate more, are enormous. Normally I'm measuring kilojoules. So that's why that value is in joules. If I divide it by this number, I will get it in calories. So that in calories will be 32,000 calories. Alright? So there you are. Now let's suppose I melt all the ice. Now I'm gonna heat it, and now I'm gonna boil it. By the conservation of mass, you should know that all the ice you melt is all the water you will have, right? The mass doesn't create like the energy. It's not created or destroyed, it's just converted. So you just convert it to water, and now the water is gonna boil. It's not gonna disappear, it's gonna go into steam, gas. So how do we measure now the energy to boil the water? You need the latent heat of vaporization, which is 22.6. So to boil the melted ice, which is now water at 100 degrees, to boil water at 100 degrees Celsius, you need the LV, which is 22.6 times 10 to the 5 joules per kilogram. It's amazing, right? Look how much energy you need. It's a lot. Alright. So QL will be 0.4 times 22.6 times 10 to the 5. And that will probably be in the millions. No, that won't be in the millions. It could be, but 904, almost a million joules. 904,000 joules. Which explains if you ever try to boil water in the lab, it takes a long time to boil a whole bunch of, like, 400 grams is like a cup of water, right? So look how much energy you need. Alright, so that's the only thing. I mean, there are a lot of interesting stuff you can do with this. But I think that's the scope, and that will be the idea. Alright? The next section is weird, because once you do that, that will be almost it, right? We've done phase changes. We've talked about melting, boiling, condensation as well. Remember, you can go into condensation, solidification if you're going from water to ice. But we haven't really, or the next section after this will be talk about thermal machines. Which is weird is because this is in between the first law of thermodynamics and the application of the first law, which in the textbook, let me actually take a look at that, because in engineering textbooks, they tend to do this. They tend to call thermal machines, okay, this. Let me see what's in here. Yeah, I will do that. Yeah, so in the textbook that you guys have, they call the heat engines or thermal machines as the second law of thermodynamics. That's not entirely accurate. Thermal machines. Actually, let me show you the slide because we already don't know this, so that's fine. Let me show you what I mean by that. A thermal machine is no other than a nice application of the first law of thermodynamics. You can have a heat engine, you can also have gasoline, diesel, jet engines, refrigerators, right? The idea is that they use heat by burning fuel. But some of that is converted into mechanical energy, for example, to drive a car. But you should know already that every system has some sort of efficiency. Not, for example, right? The example that I gave you with you doing exercise. Not all the energy that you output is used to lift weights. Some of it is used by your body to change the internal energy of your body system, right? The energy that you have in there, right? So ideally, you want to output with the most amount of efficiency. But that's not the case. And the same happens in everyday life. So there is a remainder heat. Normally it is ejected in a machine to the air in a what we call as an exhaust pipe, right? In the cars, you know, back in the old days, or even nowadays, there is an exhaust pipe, right? Every energy device, either if it's made by coal or nuclear, right? They produce energy, in this case electricity, and they turn it into a generator. But not all that heat is used by the generator. There is some waste. In the case of nuclear, there's nuclear waste, which is not good, right? Because that's the radiation remnant. Anyway, so that heat that is sort of wasted in a thermal machine is the work. All right? So you can have a heat source. You input some energy. The heat engine outputs some energy in form of work, but then it also outputs some energy in form of in a coal reservoir. All right? So the mechanism converts some of the heat into mechanical energy and rejects the remainder. So this is a simplified version of this. All right? So if you think about it, that's the application of the first law of thermodynamics. It's not really a second law. They call it a second law because they say that a device that transforms heat into mechanical energy or work. So they define that as the heat, but we talk about that in the first law of thermodynamics. But they call it a second law because it's more like an application of the first. In science, in physics, the second law of thermodynamics has to do more with entropy, which is the measurement of the particle disorder. It's a very complex variable, right? But the simple way to understand it is that whatever you guys do in life, the principle of entropy, the principle or the second law of thermodynamics, which is the principle of entropy, is always, it always tends to be larger. All right? So even though you may be doing some, so when I say disorder, it's like it has to do with the motion of particles, with the temperature and the heat. All right? Which is why entropy is defined as the rate of change of heat as a function of temperature. But again, don't worry so much about that. So that's your thermal machine. And as it says here, right? And I was saying, no device can be built that will give you that will extract heat from some high temperature source and deliver all that heat in form of work without rejecting heat into the lower reservoir. So some of the heat, unfortunately, is wasted, and some of it is used in terms of work. So work is what we use, and QH is the heat that we receive. So there is something called efficiency of the system. There are several ways to get it. If you think about it, right? By the conservation of energy, QH is the total heat. There are two outputs in the figure. There is work and there is the heat output. So the first equation, simple, is that QH is equal to QC. This should be C. I don't know why they put 1 in here. That's 1. Should be C there, QC. So the output heat plus the work is equal to the input heat, the hot reservoir heat. So what is work? QH minus QC. What's efficiency of the system? Is the work used divided by the energy given times 100%. And let's take a look. There you are. So, not bad so far. There is something that, again, in order to understand it, you will have to, well, actually, let me try to simplify it for you guys. So, every machine has some sort of process, right? You can have a change on pressure, like it can be a gas, right? And you can have a change on temperature, internal energy. You can have a change on pressure, temperature, pressure, internal, and even volume of the gas. There is something in here that says Carnot efficiency. What is the Carnot efficiency? Let's imagine 1 or 2 processes that will give you an ideal scenario. The first one will be that no heat is wasted. Now, we know that that's not possible, but there is a process that you can apply where the change on heat of a system is exactly 0. Now, the first law of thermodynamics cannot be broken. So that means that the work is equal to what? To the internal energy by the first law of thermodynamics, right? If Q is 0, then work equals to the negative internal energy. So that's called the adiabatic process. And then you want, ideally, no change on temperature. So you will have an isothermal process. So those are the 2 processes. If you do 2 of each, you will get the Carnot efficiency. Do you need to know all that? Maybe not. But if you guys go into, and I will try to give you guys a video of this, where they explain the Carnot cycle. Maybe you guys did a lab on this. I don't know. I remember in Physics 102, we do the lab where you have the processes in there. It looks like a parallelogram, right? And it's embedded, it's formed by the intersection of 4 curves. 2 adiabatic processes, 2 isothermal processes. The area is actually the maximum amount of work you can get. And that will give you the efficiency. And the particular situation about that is that you can compute the efficiency only by looking at the change on temperatures between the hot and the cold spot, which is given here. By the way, even though it matters in this case. for heat machines and for the first law of thermodynamics, we use kelvins. All right? So that's why the temperatures have to be in kelvins. All right? Well, there's an example here with efficiencies. And let's talk a little bit about refrigerators and air conditioners. How do they work? They absorb heat, right? And then you have sometimes a pump, and there can be some heat release, right? There can be a liquid inside, can be water, or can be something else, right? In air conditioning, uses water, right? And we know why water is a good element. It's a perfect coolant. It has a high specific heat capacity, and it allows water to move and cool down elements in an engine, for example, right? So the way they work, a refrigerator, an air conditioner, is they use an input of energy. And that produces heat to move, to flow, right? So that heat that was given, it causes the heat to flow from a cooler to a warmer substance, which is opposite to the natural flow, right? Normally it goes from hot to cold objects. But remember that you gave it an input against its will, per se. So the idea with a refrigerator and air conditioner is to extract heat from an area and cool it. In the refrigerator, you cool it inside. In an air conditioner, you extract heat from your room and it cools down your room, right? So in these devices, heat is transferred from a substance being cooled, right? Or sorry, that would be for in the case for the refrigerator and for the air conditioner. It's extracting heat from an area, right? So it's going from a cooler to a warmer substance, basically. In a heat pump, now you want to heat up the interior of your house. In this case, the heat is transferred from a substance being cooled, and then a larger amount of heat flows into a different substance that is being warmed. All right? So a refrigerator removes the heat from the interior and ejects that into a room. You know what's interesting about that? That's why you have to keep it closed. Because if you guys open the refrigerator, obviously the food is gonna get spoiled, but that you are breaking the process. And then the refrigerator is not cooling down its interior anymore. What's more, when you open the refrigerator, it's going to start ejecting heat into the room. So, ironically enough, that will make the refrigerator, not the freezer by the way, but a refrigerator to start around if you open a refrigerator, maybe that has happened to you guys. When you leave the refrigerator open for so long, you will notice that after some time, some of the area around the fridge is kind of getting warmer for some reason. That's because the refrigerator is removing the heat and ejecting it. Where does it have to go? Somewhere, right? To the air, to the outside. That's how it cools down the food inside. Okay? If you guys ever wonder why the back of a refrigerator feels warm, that's why. Because it's extracting the heat and it's pumping it from the exhaust. Right? Now, you should know by now why new refrigerators. So now let's talk about transfer of heat. Right? Because these devices are called heat movers. They use energy, or they use an input of energy to cause a heat flow. So it's not a naturally occurring event, right? It's a machine that we built. Nowadays, refrigerators, when they come with a freezer, not like the one in the picture, but the big one, right? They have the freezer at the bottom. Back in the day, I actually saw one. They are not common anymore, but there used to be refrigerators where the freezer, or in my case, I think I've seen one lately, but The best refrigerators are the ones that have freezers at the bottom, not at the top. Now you can use this chapter to understand why. And it doesn't have to do much with thermodynamics or heat movers. The main reason why a refrigerator that comes with a freezer must have it at the bottom is because of how heat is transferred, right? If you remember when we talk about convection, there is something called convection cycles. So the warm air or substance, or in this case air, tends to go up, and the cool one tends to go down. So you are increasing the efficiency of the freezer by having it at the bottom of the fridge. Okay? All right. So there it is, there's a mechanism in there. And there you are. So it's sort of the other way around, right? In the case of a refrigerator it's not like a thermal machine, it's a heat mover. All right? You give the energy, and then the machine, which is called a heat mover, uses some input and start extracting heat and cooling down the environment in the case of the interior, in the case of a fridge. So now we can talk a little bit about the real second law of thermodynamics, which is that in any thermodynamic process, guys, in any event, the total entropy of the system and its environment either increases or remains constant. It never decreases. So normally it has to do with dispersed energy in a system at a given temperature. Remember that, as we have discussed in thermal machines, every process tends to have some sort of dispersal energy, right? Some sort of work, some sort of, when you do work, there's some sort of heat going to the cool reservoir. So by doing this, the entropy of the system increases. So as I explained before, entropy is basically the measure of the system disorder. Increasing entropy is associated by increasing the particle disorder. So the more disordered the system, the more its energy is spread out over different internal states. So again, that's probably kind of too much. Just remember that the entropy is a measurement of particle disorder. All right, and the symbol for that is symbol S. All right, and we have this equation, right? We can see that the entropy and the temperature are inverse proportional, right? You know why? Because as I said, the entropy is equal to the rate of change of heat as a function of temperature, and is measured in joules per Kelvin. Okay. All right, guys. So I think that will be good for chapter 5. If there are any questions, please let me know. Tomorrow, Wednesday, not really, but on Thursday, luckily I have a complete day off in the morning. So I will be offering some small office hours between around noon, actually. So before the exam. So you can enter and you can ask me questions if you have any. All right. But I think I summarized the best I could what you need to focus on chapter 5. Okay, so temperature scales, the first law of thermodynamics, thermal machines, more the theory, okay? And the concept of heat and a few applications of heat and latent heat, all right? Make sure you review yes, but there is also the latent heat curve. There it is. This figure is very important that you guys understand it. All right. Other than that, there's also a concept map here. Do you need to remember all those variables? No. Remember what is the meaning of freezing or solidification, melting, evaporation, condensation, right? Phase transitions, and what happens with the internal energy, potential energy, and kinetic energy. All right, guys? Okay, there's a parenthesis. I want to show you something that they asked me today in the morning, which is, well, we're going to go into chapter 6 a little bit. Chapter 6, just a brief introduction, and then you guys can leave. We're going to be talking about waves and sound. What is going to be the main thing about this chapter? The characteristics of a wave, vibrations, disturbances, and sound. The difference between transverse and longitudinal waves. That's a longitudinal wave. That's a transverse wave. And then some of these equations. Now I want to show you this. So I think all of you guys have done this lab, right? So if the instructions are not very clear, when we talk about, this is called a fork harmonic. So when you bump this on the floor, it does produce a sound. In fact, like that. There, right? So, oh, is there sound? Yeah.
The vibration can be sent through the air molecule actuator, vibrated by the first fork. After being vibrated,
So you are lucky that you probably are not doing this exactly in the lab, because when you put two forks together and you make them vibrate, there's a point of resonance in the lab. These 2 points are what you are focusing on. So why do you use water? Because you want to create, you see, if I change the level of water, right, you may want to put it around here, and I would say probably around here. So at 50 centimeters, you have, when a tube is open on one part, we're going to learn that you produce a wave, and that this here is half the wavelength. The wavelength is, let's go to the later slides. So when we start talking about waves, here, there. A wavelength is the measurement between the valleys or the crests. So clearly, all this is half a wavelength. So what you guys have in your lab, there, is a half. So you want to measure the distance between this point and this point. First and second harmonic. And that distance happens to be half the wavelength. So this is around what? 40, I would say 39.8, 39.5 centimeters. That's half the wavelength. Let's take a look quickly here. Caramba. So if you guys do it very quickly, oh, here it is. So 39.8 approximately times 2, that's the total wavelength. But that's in centimeters. That is the wavelength of the air due to a 440 Hertz tuning fork. Hertz is a unit for frequency, by the way. So you're going to learn, and sorry if we haven't done this yet, but in the later slides you will find that the velocity of a wave is equal to the wavelength that you are seeing there multiplied by the frequency. And look what I get. I get that value. The accepted value for the speed of sound is 344 meters per second. I believe it's also here in the lecture. Let's take a look at this here. Amplitude. Oh, it's coming all the way here. So as you can see, it's not going to be that bad, this section, but Doppler effect, diffraction, diffraction. You know what? Let's go here. So there it is, right? 343. So the experiment works actually pretty good. My recommendation is that you want to do it at different levels of water. That's it. All right. So yes, we will be doing a whole bunch of theory of waves, but the main equations are going to be related to what we do on transfer waves more than longitudinal. We sort of already studied this when we talk about Hooke's law. There are many applications for waves, water waves, sound waves, and light electromagnetic waves. Different properties are resonance. Resonance is basically this. Let me show you what I mean. Sorry. Let's put the love. You see that sound that you? There. That is a point of resonance. And that's a nice property, not just for sound waves. It happens also with water waves and with light. But we talked or we discussed about that in sound because you can hear it, right? So you can do that with tubes and water. And we use resonance also to measure different speeds, speed of air, for example, or the speed, even the speed of air in water, right? Now, a wave has a speed. Now, the first equation they give you has to do with the tension force and the linear density of the string. There, mass divided by length. But the real definition, there it is, speed of sound there. The real definition would be that is the multiplication of the wavelengths times the frequency. You may be thinking, but velocity is distance over time. That's fine, because frequency is 1 over time. Frequency is the inverse of period. So velocity is equal to wavelength over period, distance over time. The wavelength is the distance traveled by a wave in one period, right? The best way to visualize a wave is when you go to the beach and you see waves in patterns. That's basically how a wave pattern moves. We can have also a group speed velocity, but don't worry about that. All right. For now, we're looking at singular, simple waves. And then obviously they have an amplitude, which is defined by the peak. They have a wavelength, frequency, the inverse of period, and they have a speed, which is measured in meters per second. So clearly, we will be using that to study sound, resonance, interference, diffraction in the case of light, and other properties. So one of the main properties we're going to discuss maybe next class, will be Doppler effect. Doppler effect is the idea of the frequency / wavelength of sound and light changing due to a moving source. So I think for this lecture actually, there are not a lot of equations. We will do a few problems for this chapter, but there are more simulations and videos I will pass you. All right? So let's leave it like that today, guys, as just a head start for waves. Again, I will do office hours on Thursday morning after lunch, around, we'll say probably noon, probably 1 p.m. And if you have any questions for chapter 5, you can ask me. It should be clear now. There's a recording now as well, and I will also upload a couple of videos in there. Okay? And then we will start full on chapter 6, and with the aim of finishing it by next week. All right? So we can do a review a day before the day of the exam. Just so you guys know, the exam number 2 will be on Thursday the 19th. All right? And then we will have 2 chapters at least more to go, which is electricity and magnetism. All right, guys? Are there any questions about the quiz or about the lab that I just showed you?
Yes, Professor, I have a question. So the thing that you said is the speed of the sounds is depend or independent of the frequency.
It depends on the frequency, yes, because what is the lab? Did I already close it? Wait, I want to open it. Okay, so you see that?
Yes.
Water level changes, so I'm putting a 50. So these points are the first and second harmonic. They give you the half wavelength. You need to multiply by this. Look what happens if I put 512.
Okay.
Right? So my guess is that you have to do it for different frequencies. Now, if you put too much frequency, you have to reduce the water level to be able to see a complete harmonic in there. You see what I mean?
Yeah, Professor.
All
Thank
right?
you.
So you guys don't need a diameter of this guy. I don't know why they told you that. You don't need a diameter of the tube. You only need the tuning fork frequency and the different. Guys, look, if you are having questions, right? Look what I just did. This is a very nice website I want to share with you guys. It's called Hyperphysics. You can just go there and they show you what to do. If you have a node or an anti-node, this is called a node. The point where a wave and another wave meet, that's called a node. An anti-node is this. We're going to talk a little more about that later, but there are resources out there, guys, and also you can look at the experiment, right? But you can always ask me a question as well, I don't mind. I hope that you guys understood it though. All right, was it clear what you guys have to do now? Is it clear?
Yes, Professor, thank you.
Okay, all right. So office hours Thursday, guys. I will send you guys a link. They might be on Zoom. All right, so I hope you don't mind. You don't need to install it. You just click on the link and you go and you can ask any questions. All right. But again, it's just a quiz. The exam will be the one that will have chapter 4, 5, and 6. Okay. All right, guys. Have a nice evening. Be safe, and I'll see you guys on Thursday.
Thank you.
See you guys.
Thank you.